that involves the use of the diffraction grating equation. So it's giving you a beam of light, and it shows that when it goes through this diffraction grating, this beam of light, interference happens, and the first maximum that appears, which we call the 0th order maximum, is always straight onwards from that diffraction grating. The next maximum that happens from there is what we call the first order maximum. Now that happens both on the bottom end and also on the top end. So this here would also be called first order maximum. And the angle between the 0th and first order maximum is the same, whether it's below the 0th order or above the 0th order. So it says here, when the spectrometer telescope is rotated, the first maximum that appears is after 50 degrees, and say the order. Well, we actually sort of already done that. It's the first order after it's rotated 50 degrees, if theta is 50. Right. When light is directed, light emerges at A and B. State the difference, or one difference, between light emerging at B compared to light emerging at A. So the central maximum, or the 0th order, is where there's the biggest intensity. An intensity curve will always look like this. So this would be the central maximum, or surrounding maximum. The intensity, or the maximum intensity I should say, that's reached will get smaller and smaller as you go up the orders of maximum. So if this is 0th order, this would be the first, this would be the second, so on and so forth. So we say light at B would be less intense than light at A because it's the first order maximum compared to the 0th order. That'll be enough to get the mark there. Moving on to part C now. The angle of diffraction at the center observed at beam B in the image above is 51 degrees. So this angle here is 51 degrees. The grating has 1,480 lines per millimeter, and calculate the wavelength. Now this is where we use this difficult equation of d sine theta equals n lambda. The most difficult part, I'd say, is using the distance between slits, which is what this little d stands for. So if we imagine a grating, it'll have lots of lines, and every millimeter there's 1,480 lines every millimeter. First of all, we have to find out how many lines there are every meter. So if there's that many every millimeter, we have to multiply by 1,000, and there's going to be, well, 1.48 million, or 1,480,000 lines every meter. The reason we need to find the number of lines every meter is we can use that to find the distance between two of those slits, because the distance between slits is actually 1 over the number of lines which appears every meter. That's why we have to convert into meters actually, so that we can use this equation here. And this distance that we find between the slits will also be in meters as a result. Okay, I'm just going to clean some of that up, just so we have space for the working out. So that was important information. I'm just going to write that out. So 1,480 times 10 to the power of 3 lines every meter. So our equation is going to, well, we want the wavelength. So we divide both sides by n, which is the order number. In our case, the distance between slits, we already mentioned, is 1 over all of this. I'm going to put all of that here. We multiply that by sine of the angle. I think it'll be better if I rewrite this out here, so I'm just going to do that quickly. Just bear with me one moment. There you go. And then we multiply that by sine of the angle of diffraction, which is sine of 51 in this instance. And you divide all of that by the order number, which in this case is the first order, so we're just dividing it by 1. All of that by 1. Sorry, there's not much space on the whiteboard. And that will give you the final answer for the wavelength. So I'm just going to quickly do that on my calculator. This, by the way, says 1480 times 10 to the power of positive 3. So just doing this on my calculator. Sorry, I'm getting a little confused. So the numerator becomes 5.25 times 10 to the minus 7. And then because we're just dividing that by 1, that'll give you a wavelength of 5.25. Sorry, that took quite a long while. Times 10 to the minus 7 meters. Finally, we can move on to the last step where we want to determine whether any more orders are possible. Well, technically, the maximum angle of diffraction that can happen is 90 degrees. So what we do is we set theta being equal to 90 degrees, and we want to find the value of n in d sine theta n lambda when theta is 90 degrees. So let's make n the subject. We divide both sides by wavelengths. The distance between slits we mentioned is 1 over 1000, the number of lines every meter, which is 1 over 1480 times 10 to the power of positive 3 times sine of the maximum angle of diffraction that can happen over the wavelength, which we just calculated. What that will give is the maximum number of orders that can happen, because the maximum order can only happen at an angle of 90 degrees. Okay, I'll be quick on my calculator this time. Divided by 5.25 times 10 to the minus 7 gives 1.29. If 1.29 orders is possible, of course we can't have a decimal number of orders. So that means that one order is possible, one order maximum, but the second order maximum is not possible in this instance because it would go past the 90-degree angle, which we can't have. So the question asks whether any more orders could be observed. We say no. And that's the final answer to this question. If you have any questions, just let me know in the comments. Thanks for watching.